The following teacher development program is brought to you by the MultiChoice Africa Foundation.
Yeah, good job.
How's it?
Yeah, right.
Aren't you supposed to be at soccer practice?
Well, I've cancelled the soccer practice, and some of the kids are a bit shaky at the moment.
What do you mean?
Well, they were complaining about stomach aches, and one of the guys told me his sister's hair is suddenly falling out.
Are all these kids from the same area?
Yeah, we are the section C, the Bonapa and Zanzi, by the river.
But there's that new factory there. I wonder.
Oh, I thought of that too. Hell, they could have arsenic poisoning or something horrible like that.
Listen, why don't you come over, then we can look up some stats?
Okay, fine. But firstly, it's a Kali's Plaza, then I'll be there in a short time.
Okay, no, great. Shop then. I'll see you then.
Bye-bye.
Bye. Okay, let's go to the U.S. Environmental Protection Agency site. They'll have safety statistics on arsenic in water. Oh, I'll probably have to go and fetch Tulani now. Oh.
Let's see that.
Okay, then I'll see you in about 2 hours then. All right, love you, bye. Right, any figures?
Yeah, there's an announcement on arsenic. They've raised the standard. Well, usually it was 0,0000 0,00005 per liter. Yeah, but how do you read that?
Well, it's much easier if it's written in scientific notation. What you want to do is get rid of the zeros because they're confusing you, right? Okay. So it's 0,7 1 2 3 4 5 6 7, then 5 liters. It would be nice if we could move the comma after the 5.
That's 1 2 3 4 5 6 7 8, comma 8 spaces to the right.
Right. And to compensate for moving 8 digits to there, then we have to multiply by a factor of 10.
Well, what do you mean?
Well, since we moved the comma 8 digits to the right, then we have to multiply by 10 to the power minus 8.
When you move the comma, each time you move it to the right, you're actually multiplying by 10.
Mm-hmm. And to keep the number the same, when you multiply by 10, you divide by 10 again.
It's like multiplying by 1. So if you multiply by 10, then divide by 10, the number stays the same. So here I've multiplied 10 8 times. So that is 10 to the power 8 on top. So to divide, we need 10 to the power 8 below.
And if you divide by 10 to the power 8, then you write it as multiply 10 to the power minus 8.
Okay. 5 times 10 to the power minus 8 liters. Hey, I'm getting it, man. So that means the standard is 1 multiplied by 10 to the power minus 8.
That means the old standard allows for 5 times more arsenic in water than the new one.
I don't think it could be arsenic. There's no coal mine near Section C. Oh, we're exposing pollution, aren't we?
See, the thing is, it not only messes things up, it's a waste of lots of money. I mean, Mr. Emmanuel Lubimbi's kids will agree with me. They should learn about pollution in math literacy.
Mr. Emmanuel Lubimbi is teaching a lesson on data handling and recycling. It is very important to recycle aluminium cans because we can save 95% of the energy needed to make aluminium from bauxite ore. This means we can prevent most of the related air pollution like sulfur dioxide that creates acid rain.
I'd like you people to have a closer look at this symbol, which tells us about recycling. With you there? It looks like this. It shows recycling. If we recycle a can of this nature, it will save us 95% of energy. If we recycle this can, we also prevent a lot of air pollution in our environment.
Last week, Emmanuel asked the class to keep a tally of the amount of cans their family uses every day for a week.
And here is the total per person, and my family drink a lot of drink.
They listed the amount of cans each person in the family consumed every day. Now they will present this information in a bar graph.
One shows the number of days. So now we are just going to assume that, our bar graph is going to start from 0 and it will end there by 10, even though there are some families who consume large number of cold drinks. We must now have to look at on which day does your family consume large number of cans. You're just going to assume as on day 1 your family drank only 9 cans. So your graph will have to stop here. On day 2, let's assume maybe they've consumed 5 cans. Your graph will have to stop here.
Emmanuel helps the learners find a scale for their bar graphs by checking what the largest amount of cans consumed a day is for different learners.
So now you'll have now to write 1 year, 2 year, 3 up to 13. Anyone actually who comes from a family where they consume more than 13 cans.
On day 3, my family drank 15 cans.
On Monday, my family drank 14 cans.
In case of Mallory and Promise, who have consumed more than 14 cans, they'll have now to consider the small blocks now here. Your 1 will start here, 2nd, 3rd, 4th, and up to there.
When you draw a bar graph, it is important that you count the number of blocks correctly. You either use the large or the small block when you mark out the scale. Emmanuel assists a learner who is struggling a bit with this.
You consider the small blocks instead of considering the big one. So your 1 will supposed to be here. 2, 3, 4, 5, and up to 13.
Once they have completed their bar graphs, the learners can easily compare the consumption of cold drink in their family to the rest of the class. When you make a comparison, you have to take the scale into account.
Class, I want you now to listen to me now and look at this. I have Tobile's graph and Mallory's graphs. I want you now to tell me between these two families, which family consumes lot number of cans?
So it's the graph on the right, Mallory's graph, sir.
Yes, you are right. Mallory's graph is the one actually shows that, Mallory's family consume large number of cans. By just looking at these two graphs, Mallory and Tobile's graph, Tobile's graph shows, it has a tally which shows, the graph is much longer than the other one.
She's got a larger number of cans. She used those small blocks and I used the bigger ones. So it looks like mine is a bit longer.
Let me just check something here. And are you also done there? Okay. Now, Lebogang, if you can look at these two graphs, which graph shows that, which family consume large number of cans?
I would say the one on the right-hand side, because that one has more long columns than that one.
Tobile, what can you say about these two graphs, actually?
The reason why the other one's got smaller columns is because they use the smaller blocks, and the other one, they use the larger blocks, so that's the difference. She's got larger number of cans, so they all can't fit in the graph. She has to use smaller blocks.
Using Mohao's graph, it shows that, on day 6, Mohao's family consume 11 cans. Coming there to Premier's graphs, it shows that on day 1, the family consume 13 cans.
Next, the learners calculate what the average consumption of cool drink is for a family member in 1 week. Emmanuel demonstrates how this is done.
Once you're done with that, actually, from there you'll have now to add total numbers of cans which your family consumes from day 1 up to day 7. You write the total year. You'll have now to divide that particular number by number of family members. It will give you average consumption per person per week.
The learners extrapolate their results and predict how much one of their family members will drink in a year.
That is only per week. So how are we going to get it per year?
So, because there's 52 weeks in a year, sir, I think we're gonna we're gonna multiply that number by 52.
For every person in the class, this is still a lot less than how many cans the average American drinks.
An average person in America consumes 1,500 number of cans. So do we have anyone who's having a number which is not far away from 1,500?
I've got 655.
I got 416.
I'm so glad that I can see that our South African people actually doesn't pollute land unlike our American counterparts. Because you can see by just looking at the difference between 1,005 and 400 and something, it shows that we South Africans, we take good care of our environment.
It turns out recycling is not just good for the environment, you can also make money out of it. Emmanuel asked the learners to calculate how many cans their family will use a year if they drink more or less the same amount as they did in the past week.
So my family uses 13 cans a week. 13 times 52 is going to give me...
How much? 676. Tasneem, you must also take note that for 30 cold drinks cans, you'll get 1 kg. So now I would like you now to work out how many kgs are we going to get from that 676. 22,5. 22,5 kg. How much are we going to get now?
9 rand, sir.
It might sound as if it's a small amount, but imagine if each and every one of you do what Tasneem did actually. It's going to end up giving our school a lot of money.
The learners calculate how much money their group could make a year if they put together all the cans that their families use in a year. Each group writes their total on the board. The individual numbers seem small, but when Emmanuel adds it up, it is a substantial amount.
351.47 cents.
And this is just the money one class could make.
It will be 351.
Just think what they could do if they got the whole school involved and collected more cans than just the ones used by their immediate family. In the end, the learners hand over their cans to the teacher. It's a first step in starting a recycling project at the school.
Hey, listen to this. It's on the legal limits for lead in drinking water. Lead and copper are regulated by a treatment technique that requires systems to control the corrosiveness of their water. If more than 10% of tap water samples exceed the action level of 15 parts per billion, water systems must take additional steps to reduce corrosivity.
15 parts per billion?
Do you want to try and write that as a scientific notation?
Absolutely. I like moving the goalposts and the commas. How many zeros are in a billion?
Well, in the UK it's 12, the US 9, and in the US a billion is 1,000 million.
Okay, let's take the US. Okay, that is 15 divided by 10 to the power 9. And 15 multiplied by 10 to the power minus 9.
Impressive. And of course, that also happens to be 15 nanoliters.
Now what?
nanoliter. 1 nanoliter is a billionth of a liter. This is how you write it. 15, and then you'd have nanoliter in a small n, and you have your liter. Of course, then you have nanogram, nanometer.
Yeah, enough. I just want to catch a nanosecond walk, right? You see, just now.
Hey, you know, 15 parts per billion may not sound like much, but it's still too much. And I read here that most lead pollution is from lead pipes in old neighborhoods.
That rules out Section C. There are no old pipes here. In fact, there's almost nothing except for the shacks and the river.
Okay, then we'll have to test for sulfur dioxide. Hey, the water tested positive to sulfur dioxide.
And now?
Well, I've heard there are environmental organizations that can help with this kind of problem.
We spoke to Richard Worthington of EarthLife Africa. He explains that environmental activists need to understand graphs as well as percentages to be truly effective and well informed.
As an environmental activist, it is important to have a grasp of basic mathematics in terms of both individual installations that we might be looking at. One needs to be able to understand the kind of figures that project what the impact of such an installation is going to have, but more so in terms of comparing possible development paths. In addition to having a good sense of how numbers work, it does help if there's visual literacy that comes with the maths literacy. So you might get a bar chart which shows quantities in different sized columns. So it just gives you a physical representation of how the numbers relate to each other. Another popular way is to use a pie chart. Maths helps us to quantify what the impact of different population groups are on the global environment. So you can actually calculate how much resources are used per person on average in a country. And that will relate to how much waste they generate, how much water they use. So you can calculate a person's ecological footprint or a country's ecological footprint and then compare that between nations. So one of the indications that we have of the global footprint of people's energy use is this map of the world prepared by the World Resources Institute, and you'll see that the countries are all very funny sizes. We know that Africa is not actually that small compared to Europe. This is a map where the size of the continents are indicated according to their contribution towards global warming. If you want to be an informed activist and be confident about what you're advocating, yes, it is important to be able to deal with quantifications of environmental impact. As soon as you quantify something, you need to use numbers. So basic maths literacy is really important, not even if you don't want to be an activist in the sense of going out there and trying to change international policies, but just in terms of making sure that, for example, you don't get a cement factory in your area starting to put toxic waste into its kiln. You need to be able to look at their projections of what that will add to the air pollution burden in your area.
You never thought math would become so relevant to me.
So why don't you sign up for the upcoming course and then you can become a math literacy teacher?
You think so?
Yeah, I mean, you've got matric maths, and not that you're particularly good at the subject. But I mean, if a guy like you can do it, anyone else can.
How can you say that?
No, I didn't mean it in a bad way.
No, you meant it the bad way. I mean, why do you say it?
Suka man, Lebogang, just zip it.
No. I mean, yes, I'm learning math, it's fine. But if you say